Hi, welcome back. So we left in a bit of a conundrum where we didn't know what to do because there was a mismatch of this thing here talking about the context and this thing here not doing it. And the way to get out of this pinch is to generalize also this system to talk about non-empty contexts. So this is what I've done here. I didn't want to type this out live, so I prepared it. But all I've done is I've taken these three lines. They are exactly the old SK system from up here, app KS. And I've added in these two lines which talks about variables. So this is SK with variables, right? And then I just put in a context everywhere. And the context doesn't actually change, right? Just weaken or use the variable. Okay, and just as a sanity check, we can see that if we have something in the SK with variable system, but in the empty context, then that's the same as the original SK system. And this is not hard to prove. So we just pattern match on the derivation, and we have to deal with these three cases because it's the empty context. We can't possibly have any of these two, and then we see that we have all of these in the other system as well. So this is just going to turn apps into apps, and k into k, and s into s, right? And then here we do recursive calls. Okay, so that's a good sanity check that in the empty context these two things are actually the same, right? We could also translate the other way, but we're not actually going to need it for what we want to do. So now let's see if we can translate from the original system with abstraction to the SK system with variables. So now both of these sides are actually talking about gamma, right? So now I think we have some chance to do it. So that's pattern match on the D. And now these rows that deals with variables are really easy to translate over because we have them in both systems, right? So we can just translate hypothesis to hypothesis and weakenings to weakenings, like that. And we also have application in both systems. So I can translate an application to an application, like that. And the only tricky thing now is the abstraction, right? Because I don't have abstraction in this system. I have S and K instead. So the way to do this, as is often the case, is to implement abstraction at the level of S and K. So I'm going to do that in a where clause here. I'll say I have apps SK, which is going to be the type of abstraction from here. So something like this. But in the SK system, right? SKV system. So this is a very common pattern where just showing that also the target system has the same underlying structure as the thing we want to implement. So the claim is that if I do apps SK something here, it's not in scope because I didn't reload the file. These are lowercase letters, aren't they? Like that. Then that's going to give me what I want. And then what should I give to this? Well, that just looks like the recursive call on D, right? Okay, so if only we can implement abstraction for this system, then we are done. And we do this again by pattern matching on the D, right? So what do we have here? We need A implies A. Okay, but I think we can do that. That's going to be, see if an auto can do it. So it's SKK, the famous I combinator, right? Okay, oh, and as usual, the type here is underspecified. So we just have to say what B is. And we just make it A, for example. It doesn't matter what it is. Okay, if it's a weakening, then what do we have to do? Well, we have a D, so if we abstract D, then that's all the wrong context. Right, so we want A arrow B, and we have a B, so if we apply K to something, then that's going to be what we want. So what happened? We wanted an A arrow B, and we have a B, so we're going to implement that as the thing that's constantly the proof of B that we have. So that's K of D. Right. Okay, and if it's an application, then what do we want? We want A arrow B. Let's see, so S is the thing that kind of works like an application. So I think this is going to be app S of something. Except S is taking multiple arguments. Right. So here, this is going to be the thing we are applying. And here, this is going to be the thing we are applying it to. Okay, so we are implementing weakening with K and application with S. And then these two constants, this is just going to be constantly K, and this is going to be constantly S. Like that, right. Okay, so again, this probably makes more sense if you walk through it yourself slowly, rather than watching me do it. But the point is that we have shown that we can implement abstraction just using the S and K combinators, which again you might remember from combinatory logic. And now it's of course not hard to go from here to here. How do we do it? Well, we start by this. If I first use this translation, that gets me to the SK system with variables in the empty context. So if I then translate further, then that gets me to where I want. If I want to be fancy and write this point tree, I could just write this as the composition of these two things. Right. Okay, so what have we learned? We have learned that we can just use pattern matching to prove things about this logic. So just like we did for vectors or for less than or for any other thing, we just represented the derivations as constructors of a data type, and then we use pattern matching to prove it. And the concrete thing we did was we showed that S and K combinators can replace abstraction and application. Of course, you have application on this side as well. So you can prove some results that are not completely obvious this way. And often you have to introduce some intermediate data structure to do the thing you want. So there's still a lot of thinking needed for these proofs. You can't just press Ctrl+C, Ctrl+A and hope that it will work. But that's also part of the fun.